MCV4U1 Chapter 3 Applications of Derivative Session 5. In this session we are going to work on section 3.2 from the textbook, maximum and minimum on an interval, extreme values. In this section we are basically looking for maximum minimum of a function on a closed interval. By looking at this diagram, we'll see maximum minimum in this diagram occurs at the points that we have horizontal tangent line. Maximum is when derivative is 0 and minimum is at end point. Maximum, minimum, both of them are at endpoints. In summary, we can have this algorithm to find maximum, minimum values of a function on a closed interval. If a function f of x has a derivative at every point in the interval a and b, we calculate the derivative and we set the derivative to 0. Then we find the value of function when derivative is 0 and at endpoints. The biggest one is the maximum and the point with the least y value is the minimum. To extend this, we can say maximum minimum occurs at endpoint or at a critical point. A critical point is a point at which derivative is either 0 or derivative does not exist. Minimum, maximum. So we calculate the value of the function at critical point and endpoints and we do the comparison. Let's solve a couple of examples. Find the maximum minimum value of f of x equals negative 2x3 plus 9x2 plus 4. We find the derivative, we set it to 0. X would be 0 or 3. We calculate the value of function at 0 and 3, critical numbers where the derivative is 0, and endpoints, negative 1 and 5. As you see, 31 is the biggest among the y values and minus 21 is the smallest. Therefore, when x is 3, function is maximum and the maximum is 31, and when x is 5, function is minimum and the minimum is negative 21. Maximum is at critical number and minimum is at endpoint. Let's look at example 2. The amount of current in amperes in an electrical system is given by Ct equals minus T3 plus T2 plus 21T, where T is the time in seconds and T is between 0 and 5. Determine the time at which the current is at its maximum and minimum, and determine the amount of the current in the system at these times. If the derivative dc dt is minus 3t2 plus 2t plus 21, we set it to 0, t equals 3 or negative 7 over 3. Negative 7 over 3 is indivisible, time cannot be negative, therefore at t equals 3, the derivative is 0. Now we calculate the value of c when t is 0, 3 or 5. And we find the maximum and minimum. At 0 it is 0, At 3 it is 45, and at 5 it is 5. Therefore, at t equals 3 it is maximum, and it is 45 amperes. At t equals 0 it is minimum, and it is 0 amperes. Next example, example 3. The amount of light intensity on a point is given by this function, f of t equals t2 plus 2t plus 16 over t plus 2, where t is time in seconds and it is between greater or equal than 0 and smaller or equal than 14. Determine the time of minimal intensity. We find the derivative of the function, quotient rule, derivative of numerator, which is 2t plus 2 times denominator itself, minus derivative of denominator, which is 1, times numerator itself, t2 plus 2t plus 16, divided by denominator to the power of 2. Quotient rule. Derivative is t2 plus 4t minus 12 equals 0. Set it to 0 by factoring with ct is either negative 6 or t is 2. Negative 6 is obviously inadmissible. Therefore, we have to find the value of the function at 2 when derivative is 0, at 0 and 14 endpoints. I at 0 is 8, I at 2 is 6, I at 14 is 15. The maximum intensity is 15 and the minimum is 8. Now, we'll look at the calculation in a different form by writing the derivative, the function as t plus 16 times t plus 2 by splitting the numerator. And we can find the derivative, set it to 0, and find t equals 2. Same results, different form. Let's recap. The maximum minimum on a closed interval occurs either at endpoints or when derivative is 0 or doesn't exist. The algorithm for finding the extreme values for a function f of x that has derivative at every point in an interval a, b. The reason that they emphasize on has derivative, they don't want with the case that derivative does not exist. The maximum or minimum values can be found by using the following procedures. Determine f prime of x, find all points in interval a and b where derivative is 0, evaluate f of x at the endpoints a and b, and at points where derivative is 0. Compare the values found in step 2. The largest of these values is the maximum value of f of x on the given interval, and the smallest is minimum. The extension to this is adding find when derivative does not exist. Let's have a quick example in this case. Let's assume we want to find the maximum and minimum of absolute value of x minus 3 when x is between 1 and 5. We know at x equals 3, derivative does not exist. 1, 3, and 5. At 1, the value of f of x is 2, at 3 is 0, at 5 is 2. Therefore, at 1 and 5 we have the maximum value, and at 3 we have the minimum. Next session we are going to work on questions from exercise 3.2. Question 5, part D and F. Question 4, part A. and part F. Question 6, question 7, and question number 10. Thanks for watching.